appears to be coming out of the tip of the pen really smoothly. There's two reasons, major reasons for that. One is we assured that the resolution of the tablet was 2 or 3 times greater than the display resolution. And then we also have a Kalman filter for predicting where the pen's going to be in the future. So as you're moving very quickly, it's doing a trajectory analysis to determine where the pen's going to be in the future. So the ink is actually writing ahead of where the data points are coming from the tablet, and that's why it looks so smooth. I pick up some of the modern tablets and do this, and their ink is lagging behind the tip of the pen because they're not doing that. I'm going to launch Rosetta. This was also really quite unique for the time. You have to remember this is a 25 megahertz processor. This is actually a neural network, so it learns as you use it. Rosetta launch. So there it is. That worked out well. And as I mentioned earlier, we can bring up the keyboard. It's being presented in the translucent layer, and I can do anything that I would do from a keyboard. This is fairly standard practice on today's pen computers, is to have a keyboard. What's really unique, I think, is that it has the translucent layer for the inking that lays on top of any existing application without modification, and you don't have to write in little boxes in a window. So as you had your pen close to the tablet, there'd be a lot of jitter. And what we did was created a test robot that tested the pen on the tablet as it was integrated into the computer. This is what the Newton team hadn't been doing. They've been testing their tablets away from the computer, then try to put it on the computer, and it wouldn't work. But we were testing the tablets on the computer, so that we were testing not only the tablet, but also the tablet ability to recognize the pen, but also how the computer and the computer subsystems interacted with the electromagnetic fields of the tablet.